So chapter 2.2, 2.3. Okay. This is about postulates and diagrams. And these postulates that we're going to be considering first of all are called the postulates of Euclid. This is Euclidean geometry. He's the guy that kind of brought everything together and put it all in one place, all in one book. Okay? And so we call it Euclidean geometry. He did not invent it. He wasn't the one that come up with most of the ideas or postulates or theorems. They were already known, but he did come up with some, and he formalized it all, and so we call it Euclidean geometry. This, by the way, was over 2,000 years ago. So I'm not teaching you anything new. You should be able to do this, right? If someone 2,300 years ago could do it, you can do it. Okay. So, remember, a postulate is just an idea that is so simple that we can't even prove it. We just have to look at it and go, yep, that's the way it is, okay? Now, we began talking in this class about points, right? Points, lines, and planes, which are undefined terms. We have no formal definition for what they are, but we all have an agreement about what it means, okay? So that's what we have to begin with. And now we have a few of the basic postulates we want to talk about. So on page 84, there's this one called the two-point postulate. And it says, through any 2 points there exists exactly one line. Well, what does that mean? Through any 2 points there exists exactly one line. Let me just draw a couple of points here. Okay, look at those 2 points. How many lines pass through both of them? One. Okay, so through any 2 points there exists exactly one line. And that's just a way of saying that defines a line, right? If I name this line, if I name it line AB, is there any question about what I'm talking about? Is there any other possible line AB? No, that's it, okay? And so there you go. Now the other one's even a little weirder. It's called the line point postulate, and it says a line contains at least 2 points. I want you to think about that for a minute. How many points do you think are on this line? At least 2. Now I know you all said infinitely many, and I get you to say that a lot, right? But aren't there at least 2? And if they're not at least 2, is it even a line? No. So I know that's a weird way to think about a line, that it contains at least 2 points, but that's the truth. That's what it contains. Now, does it contain more than 2? Yes, at least 2 though. If you don't have 2, you don't have a line, do you? And I think that's the real key here is, if you don't have 2 points, you don't have a line. Do you understand? I don't see your foreheads all wrinkling today. You look slightly unhappy with me, which is normal, but not the wrinkling forehead, so that's a good thing. Okay, now, the line intersection postulate. By the way, do you notice these all have a number next to them, like 2.3? Don't put 2.3 down as a reason for something today on today's assignment. That's just chapter 2, third postulate for this book. That doesn't mean anything. Okay, I want you to write out the line intersection postulate, which says, if 2 lines intersect, if they intersect, then their intersection is a single point. They have 1 point in common. Do you understand? If 2 lines intersect, then their intersection is exactly 1 point. Even even if the two lines are like this. Now, doesn't it look like they have a lot of points in common? But how do we define a point? How wide is a point? Right? They're so tiny that there's still only one where they intersect. Okay? So that's what that postulate is talking about. Now, I'm not spending a whole lot of time on these because they're not real complicated. They're just basic ideas that we're going to build from. They're postulates, right? Okay. The 3-point postulate. What do you guys think of when you think of 3 points? A plane, right? How do we name a plane? Well, we name it with 3 points. Why do we name it with 3 points? Well, because if I have 3 points that are not collinear, how many different planes can pass through all 3 of them? There you go. One plane can pass through all 3 of them. If there was more than one plane that could pass through all 3 of them, how could we use those 3 points to name it? Because it could be we wouldn't know which one we were talking about, right? Okay. Through any 3 non-collinear points, there is exactly 1 plane. Through any 2 points, there's exactly what? 1 line. And through any 3 non-collinear points, there is 1 plane. Now, they have to be non-collinear. I mean, if I have point W here, well, I can't name a plane with those 3 points because there's more than 1 plane that can pass through them. Right? Okay. And then the other one is, okay, if a line contains at least 2 points, then a plane contains at least 3. Now, can you think of it? Yeah, it has infinitely many, yes, but at least 3. Can we say it that way? Okay. The plane line postulate. Okay, let's say I have a plane here, and I have a line, and the two of the points on the line are in the plane. Well, what about the rest of the line? This is the part where you guys say something. If 2 of the points on this line are yeah, they're also in the plane, aren't they? Okay. So if 2 points in a line lie in a plane, then the line containing them, the entire line is in the plane. All of the points on the line are on the plane, or in the plane, or contained within the plane, however you want to say it. Simple? If it seems super complicated, we're not doing it right. Okay? And then finally, if 2 planes intersect, then their intersection is what? Isn't it a line? So like the wall over here and the ceiling. Can you guys all see where that intersection is? Okay. What about 3 planes intersecting? Could it be a line too? Like, for example, could I have another plane that comes up here and passes through that same line, so all 3 planes intersect along that line? I could. But, okay, let's take this wall and the wall here and the ceiling. What's the intersection? It's a single point, isn't it? So it's possible for 3 planes to come along and have an intersection that's a single point. So you notice there's no postulate that talks about the intersection of 3 planes, because that's complicated. It depends on how they intersect. Okay? If it's complicated, is it a postulate? No, it's not a postulate. Okay? So we don't have to do that one. Now this is a tough assignment. You're going to have to really think on this one. Look at the top of page 85. If, and then there's this picture of these two lines like this. And then it says then, and then there's the same picture of the two lines, but there's a red dot right here. And your job is to figure out which one of the postulates we talked about matches that picture. What could it be, Jesse? What's that? The second picture. So it's the third one we talked about. What's its name? The line intersection postulate. Do not tell me postulate 2.3. I know it's going to take longer to write, but I lied about it being hard. So if it takes a little longer to write, it's not so bad, right? Okay, let's look at B. If, okay, now there's these two planes intersecting, and then it says then, the two planes intersecting, only the intersection is this red line, and Jabri knows which postulate that is. Right? Yeah. Which one is it? The plane intersection postulate. This is rough, huh? Okay. Let's look down at example 2 for a minute. As you look at that particular picture, all of the postulates we talked about today are in there somewhere. There's a line, AB, right? So we have a line defined with 2 points. We have 2 lines intersecting at a single point. Line AB and line M, they intersect at a single point. We have 2 planes intersecting at a line. We have a plane that we can name with 3 points. A, B, C. You guys all see plane ABC? Right? So all of the postulates are somewhere in that picture. Okay. Now, let me show you something here. I'm going to dig it out because I've already done it once today. Okay, let's say I've got these 2 equations. Are these 2 equations linear equations? Yeah. Okay, how do you know? See the x and the y? See how they're both to the first power? So these are first degree equations. That means when we graph them, the graph will be a line. If one of these was squared, or both of them were squared, not a line. Then you get curves and things, okay? So that's how you know it's a linear equation, is x and y are both to the first power. So I have a system of equations, 2 variables, okay? 2 variables, 2 equations. How many different ordered pairs will satisfy the top equation? At least 2, but probably more than 2, like infinitely many. What about this one? How many ordered pairs will satisfy it? At least 2, but actually infinitely many, right? But how many ordered pairs solve both of them, make both of them true? 1. This particular one right here. 4, 3. Negative 3/2 times 4 plus 9 is 3. 1/2 times 4 plus 1 is 3. This is the only ordered pair that will satisfy both of these equations. And how did I find it? By graphing. I solved this system of equations not by substitution, not by elimination, but by graphing. Y-intercept's 9, down, let's see, down 3 over 2, down 3 over 2. Is this making your brain hurt because you haven't thought about it since last year? We're going to do more of it, down 3 over 2. Here, y-intercept's 1, up 1 over 2, up 1 over, hey! See that point right there? That intersection The only point the two lines have in common, right? That is the solution. That's the number, the combination that satisfies both of them. Who's solved by graphing before? Who's done that before? Okay. There's going to be a question, and you're not going to have to do this, but you're going to have to understand the concept to be able to answer the question today. Okay? So, today's assignment. Not hard. Oops.